All right, now, but you do see that this that these CO molecules are in the form of a little person. This does not represent, in the most au courant language, intelligent design. Rather, this represents the work of a very patient experimentalist, i.e. graduate student, who spent 24 hours, and I know this to be the case, 24 hours moving these CO molecules into this particular arrangement. So how did he do that? Okay, well, how he did that is the following. What he did is he takes his platinum surface and then opens up a bottle of CO in the vacuum chamber, or lets some CO into the vacuum chamber, and the molecules just absorb anywhere they want to on the, well, sort of anywhere they want to on this platinum surface. And so first of all, he's got to figure out where the molecules are. All right, so the balls, the soccer balls are the CO molecules. And the tungsten tip here is my leg and my foot, okay? And so the first thing he does is he scans the surface, right, in order to figure out where the CO molecules are. And he goes, okay, I know where they are. So then he brings his tip down and right next to one of the CO molecules. And then he gives that piezoelectric crystal a pulse of voltage, which jerks it, and hey, the CO molecule goes flying away. Well, that's nice, but now where is it? So again, you got to go scan along the whole surface to find it. And well, he pushed it over too far, so now we got to come over here, put the tip down, give another voltage pulse before his tip breaks. And well, you get the idea. 24 hours later, ta-da, you got it. Okay. So this is the beginnings of nanotechnology. You can see that it's going to be a long time before manipulation of individual atoms and molecules like this, one at a time. It's going to be a long time before that competes effectively with synthesis in a beaker, right, where you get the molecules right where you want them because of chemistry, instead of this mechanical manipulation. Okay. Well, even though these observations here, well, even though 100 years ago these direct observations of atoms and molecules was not possible, it was by the late 1800s pretty well accepted that, or the evidence for the atomic structure of matter, atoms as the most basic constituent of matter, that indeed was, that evidence was really pretty compelling. And in fact, by the late 1800s, it was basically believed that the theoretical structure of the universe was complete. Nature was understood. There were no big discoveries to be made yet. And in fact, there was some justification for that attitude. Because certainly by the late 1800s, Newtonian mechanics, the mechanics that described how bodies all around us move, including astronomical bodies, well, that had already been known for over 200 years. Thermodynamics was formulated already by that time. Statistical mechanics was also formulated by that time. Statistical mechanics is a field that relates the microscopic description of matter to the macroscopic behavior of matter. And very importantly, there were experiments by Young, Fresnel, and Hertz that seemed to put to rest the notion that light was a particle. Hey, those experiments really nailed, or seemed to nail, the idea of light as a wave. Light has wave-like particles. They verified Maxwell's equations that unified the fields of optics and electromagnetism. So all of these accomplishments surely did justify a very proud feeling amongst the scientific community. And at that time, the feeling was that the work that remained was largely to investigate the next decimal place. That's it. Well, if you look really carefully, though, at the evidence, even with all of these accomplishments, if you look very carefully at the evidence, there were beginning to be, in the late 1800s, some experiments that were suggesting that, one, well, maybe the atom wasn't the most basic constituent of matter. That's the first set of measurements that indicated something was amiss. The fact that the atom wasn't the most elementary particle. And we're going to look at these sets of measurements. And second, the other observation that hinted that this classical thinking was amiss is the observation of the photoelectric effect. Because the photoelectric effect, what it did is that it showed that light was behaving like a particle and not a wave. And that sent a lot of consternation throughout the scientific community. So we're going to look at these two tracks. And we're going to start by talking about the fact that the atom isn't the most basic constituent of matter. That at least you can divide the atom up into an electron and a nucleus. So we're going to start here with this gentleman, J.J. Thomson. Remember that name? That's going to come back. Discovery of the electron. And this is 1897. What J.J. Thomson was interested in doing was understanding what a discharge was, or what made up a discharge. So, for example, if you have a glass vessel that you evacuate, and then you have a cathode in that glass vessel, and you have an anode in that glass vessel, and you also put some molecular hydrogen in it, fill it up with molecular hydrogen. But now what you do is you put a negative voltage on the cathode and a positive voltage on the anode, and you crank up the potential energy difference, the voltage difference between the cathode and the anode. And you keep cranking it up, and you have to get really pretty high, but at some point, all of a sudden, what happens is that the gas here begins to glow. And you have the establishment of this discharge, this plasma. And J.J. Thomson was just interested in finding out what was in this plasma. Right? So what he did to investigate it is he punched a hole in this anode right here, and he let out a little bit of this plasma, and he let it impinge on a kind of phosphor screen here. So even though this plasma leaking out was kind of glowing in the dark, well, when it hit the phosphor screen, it also was glowing when it hit the phosphor screen. That lit up.